There are four different types of conic sections. There's the circle, the ellipse, parabola, and a hyperbola. And each of these conic sections is obtained by slicing a cone at various angles, at various heights up and down the cone shape. The link that you have here in your notes is going to take you to an interactive tutorial on how to achieve those different shapes by slicing the cone in different locations and changing the angle of your slice. I'm going to show you another interactive tutorial where you will see what these shapes look like as the cone is sliced. And so we're slicing this cone with a plane, or think of it as a sheet of paper. And when we change the angle of our sheet of paper, it's changing the type of conic section that we achieve. So the conic section is just that cross-sectional area that you see highlighted. There is the circle. Now you're getting the ellipse when you tilt the plane. That's the ellipse, followed by the parabola right there. And then when you take it up further, there's your hyperbola. The hyperbola is given in two branches. There's two branches to the hyperbola. And so you can see that as you change the angle of the cones slicing through the cone, or the plane slicing through the cone, you're getting a different conic section each time. And you can slide that turquoise colored plane up and down to get different cross-sectional areas. Conic sections are seen in real life in lots of different cases, and so I've pulled up a few tabs for you to see some of those cases where we're going to maybe observe conic sections in real life. So this is the Eiffel Tower. The bottom of the Eiffel Tower is a parabolic shape. The part that you can see through at the base is a parabola. This next one is pretty familiar. This is the St. Louis Arch. That is a parabolic shape. The satellite dish that you see below is also a type of parabola. It's in 3D, however, it's three-dimensional. We call that a paraboloid of revolution, and we will see that shape come up in some of our examples when we do applications. Next up, you see the cables on a suspension bridge from the top of one tower to the top of the next tower. That cable that spans between is in a parabolic shape. Here, this was a fun example where somebody decided to fit a conic section to the curve of a banana. So that is an interesting example. Down here below, you see the roller coaster could be thought of in terms of a parabolic shape, either as you're going up or you're going down. That is going to be a parabola. A football is another example that we'll come across in applications. That would be considered an ellipsoid of revolution, which is a kind of an ellipse that's been spun on that center axis that goes straight from one tip to the other tip of the football. You spin it, and then you get this three-dimensional shape. Parabolas. Once again, we've got the St. Louis Arch. Below that, you see the ever famous McDonald's arches. And let's see if I've got a couple more here for you. Oh yes, so on the left we see an application of the hyperbola. Those are nuclear cooling towers, and the left side and the right side are going to be where you get your hyperbola. And finally, we've got the Pringles chips or the Lay's stacks. Either way, you could consider these hyperbolic paraboloids. So those are conic sections in 3D as well. So those are some fun examples of where parabolas or conic sections in general could be seen in real life. So you can see it's all around us. You're going to be looking at things in a different way now that you've had this lesson, or after you've gone through this lesson on conic sections. You're going to notice them in the real world a lot more than maybe you did before. So this section 9.2 is focusing all on the parabola, right? So we've talked about circles already. We've dealt with circles here and there in other classes, especially geometry. So we're not going to focus any of our attention this semester on the circle. We're going to jump to the parabola. So parabola is made up of a series of points that are formed by connecting or thinking about the distance from an imaginary focus point. This imaginary focus point is colored in orange right there. I'm going to label that F. So if I take the distance from my focus point and compare that to the distance to, let's go from the focus point up to this point here, right? That's a fixed distance. We'll call that point P. And if I look at that distance and compare it to the distance straight down from P, we'll call this point D. The distance from F to P, that length, is exactly the same as the distance from the point P down to this pink line where I've put my point D. Now, the focus is called point P, or sorry, the focus is F rather. P is a point on the parabola. D is known as your point on the directrix. So I'm willing to bet that not many of us have heard of the word directrix before, but a directrix is kind of an imaginary line, just like an asymptote might be thought of as, but it's in this case, the directrix has a use when you're constructing your parabola. Every single point along this parabola is constructed so that the distance from the focus point to this new point, call this P, if this is P1, we'll call this P2. The distance from the focus point to each point on the parabola is the same as the distance from the point on the parabola perpendicular straight down to a corresponding point on the directrix line. And so the same thing could be said about this point that's located here. Call that point 3, and this will be point D3. And so all of those individual distances, for example, this distance is equal to this distance, and the distance here is the same as this distance down there. And so that is how your parabola is constructed, with those distances in mind. All right, so we've got the focus and we've got the directrix. We've got the focus, we've got the directrix. That's the new information we've just acquired. The parabola can be situated in lots of different ways on the XY axes, the coordinate plane. We are going to first talk about what happens when the vertex is at the origin. So on that first graph on the left here, this is the x-axis and this is the y-axis, okay? And so the vertex, which we know is that point where the parabola curves, that is going to be at the origin for these few examples that you see here. So the first parabola for graph A, you see it's opening to the right. And the graph B, the parabola opens to the left. Graph C, the parabola opens up. Graph D, the parabola opens down. Let me catch up. This goes right. This one goes left. And we are going to know from the equation of the parabola which way it's going to open. And whenever you have a y squared, the y is squared, the y is squared, the parabola is going to either open left or right. And it's going to open to the right if y squared is equal to a positive quantity, some positive quantity. And it's going to go left if it's equal to a negative quantity. Okay, so that's how you know if it should go left or right. Up and down is what we're more familiar with. We've seen that quite a bit. It's going to open up or down if the x is squared. X squared and x squared, that tells you it's going to either open up or down. And we've already learned that if it's equal to a positive quantity, it's going to open up. And if it's equal to a negative quantity, it is going to go down. Now, this coefficient that we're calling A is a new concept. What is A? A is the distance from the focus point F to the vertex. So the distance from the point F to the vertex is A, and that is super important. We definitely want to make sure that we understand what A is all about. A is the distance from the focus point to the vertex. A is the distance from the focus point to the vertex. So if you look at graph D, let's use that one as our example. The distance from the vertex down to F is A. That distance right here is A units, whatever it is, okay? However many units you want to talk about. That's what A corresponds to. Now, the cool thing is that, remember how I said that each point on the parabola is constructed so that it's the same distance to the focus point as it is to the directrix line? Okay, so the point V has been plotted for you. The point that corresponds to F is directly below it. The point directly above it, I would call D. All right, so whenever I say D, I'm referring to some point that is on the directrix line. Okay, so D is a point that's on your directrix line, and then each point on the parabola is constructed so that the distance from a point to D is the same as the distance from that point to the focus. Now, if we've just decided that the distance from V to F is A units, the distance from V to D, well, that's also A units. And so the A is consistent in both contexts. A is the distance from the focus point to the vertex. We don't have to keep the vertex at the origin. We're going to move it up, down, left, right, all different directions, okay? And so that vertex can be anywhere in that coordinate system. It could have any ordered pair. We call the general coordinates of a vertex HK, and that's something you'll have to remember. HK is the coordinates of the vertex. H is the x coordinate, K is the y coordinate. Now, something else that I want to point out that I haven't mentioned yet is that the focus point is always inside the parabola. The focus point is always inside the parabola, okay? So if you look back up at our examples from the first page, the focus points are always inside the parabola. Here, your focus point on the leftmost graph is inside the parabola opens around the focus point. Here, the parabola opens around the focus point. Here, it opens around the focus point. So that's going to be true. That's always going to be true in general. The focus point will always be inside the parabola. So for that reason, we have no other choice but to say that the directrix line is on the opposite side of the vertex, right? So if the focus is inside the parabola, the directrix line is outside the parabola. So the directrix line is consistently on the outside of the parabola. The parabola will never cross through the directrix. And that's how you know where the focus goes and where the directrix goes. The general form, and I'll get to these general forms more, but for right now, the general form of a parabola who has a vertex at HK and opens up is right there. So right here, this is out of your book. This would be for graph C from this section. It's x minus h quantity squared equals 4a times y minus k. That's the general form of a parabola who has a vertex at hk and opens up. And I'll get to all the general forms shortly because your parabola is either going to open up, down, left, or right. And each one has its own general formula. The ordered pairs for the focus and the directrix line, I do not memorize those. I like to go with a graph. And so once I've got my graph, I can see what the ordered pairs should be for the focus and the directrix line. I don't worry about memorizing those. It's not necessary. Sorry, I lost my page. There it is. So don't worry about memorizing the ordered pair for the focus or the equation of the directrix line. It will be clear once you start sketching your graph what those should be. Okay? But the general form for the type of parabola you're working with, you do need to understand, not memorize it. I'll give you a formula sheet, but you will need to know how to use it. All right, we're going to do a quick proof, right? So we're going to do a really easy proof where the vertex of my parabola is at the origin. All right, there's my vertex, it's at the origin. So if you wanted to make a note of that, the vertex has ordered pair 0, 0 in this example, but you can move this around to wherever you want to, and the proof would still follow the same pattern. All right, so what we're going to prove is that this parabola that you see here, sketched in red, has this general form, okay? So the vertex, like I mentioned, is going to be at the origin for this proof to make sense. Now we've got 3 specific ordered pairs we need to identify, 1, 2, 3. So the first one I circled is the focus. The next one is an arbitrary point. Call it whatever you want. Put it wherever you want on your graph. Call it point P. And then down here is the directrix. Now, I don't think I drew this quite to scale. I think that directrix should have been a little bit higher, but we're going to go with it. We need to identify those ordered pairs. So we need to figure out the ordered pair for the focus, for the point, and for the point that's on the directrix line. All right. The focus, remember, if this is the origin right there at the center, the distance from the vertex to the focus point, remember how we said that was A? The distance is A. And so the focus point with the graph in this position is going to have ordered pairs 0, comma, A, 0A. Point P, we're just going to call X, Y. X and Y can be anything. And then point D. Now, D has specific ordered pair. Now that we've chosen XY for point P, that makes this quantity, that distance from the origin, that makes it X units. Okay, and so point D, notice how that's directly below point P. So point D's X coordinate is also whatever X was. Once you've decided X for point P, that's also the same X for point D because they're right above each other. Now the Y coordinate, remember the distance vertically down to the directrix line from the vertex, that's also A units. And so to plot point D, I would have to go to the right X and then down A units, down A, whatever A is. All right, so what we want to do now is come up with an equation that relates this information. And we're going to use the distance formula. Do you guys remember the distance formula? Let me jot this down above. The distance between any 2 points is going to be the difference in the X coordinates squared plus the distance, oh, I made a mistake. The difference between the X coordinates squared plus the difference between the Y coordinates squared. And we're going to take the square root of that quantity. So that's a review. Hopefully you remember this. Recall distance formula. If you forgot, I just told it to you, so now you're good. And so what we're going to do is also remember that a parabola is constructed so that the distance from the focus point to point P on your graph is equal to the distance between that point P and your directrix point, okay? So that's why we needed the distance formula. So in other words, the distance between F and P is equal to the distance between P and D. Okay, those two distances have to equal each other. So let's first find the distance between F and P. So we're going to say this is the distance between, we'll go F, comma, P. And so according to our distance formula, we subtract the X coordinates, square that distance, and then subtract the Y coordinates, and then take the square root of all that. The distance between P and D, same idea, you subtract the x's, x minus x, square it, then subtract the y's, y minus negative a, square that, take the square root. Now the parabola is constructed so that these two distances have to be equal to each other. So I'm going to make an equation that's going to have, and I'll drop the square roots, right? Because if I have the square root of something equal to the square root of something, I can square both sides. And now the square roots are gone. We're good with that? So no more square roots. I'm also going to simplify slightly. For example, 0 minus x, well, that's just negative x. And when you square negative x, you get positive x squared. Okay, so that's one distance expression. The other distance expression, okay, x minus x, that's 0. 0 squared is 0. And then y minus a negative a is the same as y plus a. And that quantity is squared. Now it's just a matter of simplifying. So I'm going to FOIL the a minus y squared. So I get a squared minus 2ay plus y squared. On the other side, I'm going to FOIL y plus a. I'm going to get y squared plus 2ay plus a squared. And I am simplifying. So I notice that I have an a squared on both sides. Those cancel out. I am going to cancel out my y squareds. Those are on either side. And so those are gone. If you subtract y squared from both sides, it's what, 0. Okay, so this leaves you with x squared minus 2ay equals positive 2ay. And now your last step is to add the 2ay to get it to the right-hand side. And now I have x squared equals 4ay. And if you recall, that's what we were told to prove. So we got that done. So we began by labeling the 3 points with their ordered pairs. We labeled point F, point P, point D appropriately. P we labeled X, Y. To come up with the ordered pairs for F and D, we had to recall that A is the distance from the focus to the vertex. There's a part down here at the very bottom of your sheet that says to prove that y squared equals 4ax. I'm going to ask you to go ahead and do that on your own paper. And we will ask, let's see, let's make that due for a grade. Let's make that due for a grade on, I'll give you till Monday, which is the 13th. And we'll give you till 3 p.m. That way, if you have any issues with it over the weekend, you can log into the Zoom office hours from 2 to 3 and get some help if you need it. So submit that by email. Email me a copy, scan your paper, email it to me by 3 p.m. on Monday, April 13th, so I can see your work. Here's to get you started. What you're going to begin with is a parabola. Once again, you can put that vertex at the origin, but this time it's going to be opening to the right because it's y squared equals a positive quantity. We learned on the first page of today's notes that means that's a parabola that opens to the right. So I'm not gonna fill in anything else. I'm gonna let you guys see if you can understand. You're gonna base your proof very similar to what we've done right there when we proved the equation of the parabola that opens up was x squared equals 4ay. So very, very similar proof. Label your ordered pairs for F, P, and D. And once again, you can still use x, y for your point P. And then don't forget what A stands for. Okay? This is a great time for a break. So I'm going to pause here and we'll come back and pick it up where we left off.